So really, I want to prove that the dimension of the zero divisor of x is indeed the extension f over k of x. But to do that, I need to take a little bit of a detour and talk about what's called integral elements. We will see much more of that later when we talk about extensions. So far, we're just trying to understand a function field. What can you say about a function field? Later, we want to extend them. Because how can you understand a function field the way we do this, we start with something we understand, like the rational function field, and extend it. So that will be a key, that will have a key role there, but here I'm just using it like kind of weakly. So let's say, I'm just going to state a little lemma and prove it. So let's say that you have a ring extension, something kind of different than what we had so far. Just two rings, okay? So an element x in the bigger ring is said to be integral over the smaller ring. I never know if you should like do this also. If there exists a monic polynomial coefficient coming from the little ring such that f of x is 0. So let's see. You have two rings, S and R, and you take an element here, which may not be in R, but you are saying that this element is integral over R if there exists a monic polynomial, emphasizing monic, a monic polynomial over R, namely coefficients in R, that x is its 0. Very similar to algebraic, the notion of algebraic element, right? If these were two fields, then the exact same definition will give you algebraic, right? X is said to be algebraic over R, if this was a field. If there is a polynomial in a field, you don't require it to be monic because you can always just, divide by whatever you want, but you can say monic if you want, such that f of x is 0. So here it's just the same thing for rings, with this little monic thing that really captures the fact that you can divide with whatever you want in a ring. So that's kind of the proper definition for algebraic over rings. And it's called integral, for a good reason coming from number theory. It's like essentially the integers, but no, never mind. Okay, so that's essentially algebraic. Okay? In fields, you can divide. So, and of course, you can multiply and add, so polynomials are there. But in rings, the whole point about a ring is what can't you divide by. So this is kind of embedded there. Monic can be somehow replaced with some other things that maybe are more natural, but monic is the right way to go. It seems like an arbitrary choice of how to encode the fact that we work in rings, but it's not. It's equivalent to other things. So here is a claim, and I'm going to prove it, but okay, so let's see. So this is a little bit of a detour for like 10 minutes, okay? Usually, like in math, they assume you know all that and just start. I want to make sure that we know all that. So let f over k be a function field. Right, in function fields, you also have rings, like OP is a ring and stuff like that. So you'd expect that. And let x be any non-zero, non-constant function, and take some maybe n other functions. Then, so first of all, and that's actually completely obvious, I just want to state it, if y1 up to yn are linearly independent over the rational function field in x, then this is linearly independent over K. Okay, this is obvious, but let me just say what's written here. Say you have this n plus 1 function x and y1 up to yn. Technically, x can't be constant, but okay. And what I'm saying is that if these functions are linearly independent over k of x, not algebraic, just linearly independent over k of x, so you're allowed to use rational functions as coefficients trying to make this vanish, and you can't, so if they're independent, then what I'm claiming is that if you take these sets of monomials, infinite sets, like x to the I for any I, and the yj's, they can't be, so they are linearly independent over k. Right? Because if they were linearly dependent over k, you could cook up functions from here, even polynomials, that will make a linearly dependent between the yi's. Right, so that's just obvious, but I just want to state it so that we'll see it. Okay. And point 2 is not obvious. There exists some g of x, non-zero polynomial in x, such that g of x times y1 up to g of x times yn are integral over k of x. What I'm saying here, I'm saying, y1 up to yn are, without 1. Just it has nothing to do with 1. I just need both of them. y1 up to yn are just, these functions. They may or may not be integral over k of x. Namely, for example, y1. It may be the case that there is a monic polynomial over k of x which makes y1 vanish, and maybe not. I don't know. But what I'm claiming is that you can kind of, take the product of the denominators high enough, in a sense, so you can find a polynomial g of x non-zero, such that after you multiply those functions by it, they will become integral. It's like clearing denominators, in a sense. You can multiply them, you'll see in the proof. You can multiply those yi's by a certain polynomial that will make sure that all of them are integral. I think if you understood the statement, when exactly, the only thing here is that I want the same g. Right, but you're right. Once I found g1 for y1, and I can just multiply them. So I'm going to prove it only for 1. You're completely right. So again, so our goal is, I'm going to do it for 1. It's the same. So given a y which may not be integral over k of x, prove that there exists a g polynomial such that when you take the product is integral. And I think, okay. And you're using the fact that it's a function field, not true in general. I mean, you only need one little thing. So in a function field, right. I'm not saying this is a monic. I'm saying that this is integral. Right. Namely, there is a monic polynomial. Good. Yeah, it's confusing because everything here is a polynomial. Like when you do number theory, the polynomials are polynomials and the numbers are numbers. In function fields, everything is a function. Everything is a polynomial. So these are functions, and the polynomial that makes sure that this is integral is also a function. Yeah, so it's the hazards of the field. There is nothing that's not a function. Right. So, but again, what I want to prove is, I'm going to take just this one. So I'm going to prove that for any y and any x, essentially, well, x is not constant, but other than that, you can maybe push y a little bit upwards by taking its product with some polynomial that you can find over in x, such that this is the root of a monic polynomial. Okay, so I mean, how would you do that? You kind of start with the fact that it's algebraic, and then have the non-monic polynomial and make it, in a sense, monic. Not really, but you see. So we know that because it's a function field. I mean, I think the proof is more insightful with the statement. So we know that because that's a function field. And so that in particular implies, and that's all I needed, is that this is algebraic. Right? Finite extension are algebraic, not the other way around. So it gives you a polynomial, like namely, you can find rational functions in X, like here. Maybe some number, let's call it d minus 1. I don't know, I call it d minus 1. Not all zeros, such that y to the d plus fd minus 1 of x y to the d minus 1. That's the minimal polynomial or something. Right, because y is here and this is an algebraic extension, you can find this monic polynomial, right? I mean, it's not good for you. I mean, these are rational functions. You can't just multiply. You would say here this is the monic polynomial, but no, these are rational functions. That's not fair. You need to, if you want to make them polynomials, what you need to do is to multiply by the common denominators, and then it's not going to be monic anymore. So it's not what I'm doing, and I'm really not claiming that y is integral. I'm claiming that some other polynomial times y is integral. So that's fine. I just need to kind of be smart about the next step, but it's a little trick. So, right, it's just the degree of like y over k of x, like the degree of the irreducible polynomial. I mean, y is algebraic. It has a irreducible polynomial, a minimal polynomial of y over k of x rational function. Yes. It's not important, but I need it just because I have to wipe. So if we do take the product of all the like denominators, then and call them g, then we get that and take the product. Then you get something like this. I skip the x. But if we just take the product with of I multiply d times. Yeah, good. Sorry, that's the point. Good. So if I multiply once, it's not going to be true. So I'm taking the common denominator and multiply it to the power of d. Good, thanks. So that gives me gy to the d. And when you see you split the g's, you have d to the d, but you write 1 here and d minus 1 here. And at the end, you write all of them kind of outside without there is no y. And from here, you see, oh yeah, this is true. Like this is a monic polynomial, the same monic polynomial. No, this is a monic polynomial. So this is, you call this t. Right? So this is a monic polynomial. If you want to see where, like over k of x, that g of x times y vanishes at, I don't know, it's a monic that makes it vanish. The product of all the denominators of the f's, right, just to make them coming as polynomials. So you see, both the element and the polynomials are coming from G, but that's fair. And you can do the same simultaneously to all the yi's. You can just take the product of all of those or something. So don't worry about that. So next. So why do we like it? So let me maybe I can show you. Okay, this claim kind of tells you why you might care about integral elements in our setting and context. So let's say that f over k is a function field, and you take x in f, and assume that y is integral over x, over k of x. In a second, I'll give you an example so that you can appreciate the integrality. But even that will tell you that you appreciate it. Then what I'm saying is that for every prime divisor, if x is defined at that prime divisor, there's no poles, then also y. Right, so if you have a function that is defined at some point, you can find other functions that are defined at some point, namely all functions, like y's, that are integral over k of x. And I'll give you an example and a counterexample, and you'll appreciate the monicity or monicticity of the requirement before proving the claim. And I should put it in the notes also, the example. I keep forgetting doing that, I'll do it. But so for example, let's look at this polynomial. Like t squared minus x. So this is a polynomial over k of x. It's monic, like in t. And really its roots are the square root of x. Right? This is what it is. And what this theorem tells you is that if x is defined at a point, also square root is defined. That's right, right? I mean, you were worried about minus I or something, but I mean, it is defined. And you might be worried about branch cuts or something, but I don't, it's local, so I don't worry about that. But right, so, I mean, y here is like, let me write it like that. I mean, that's how we kind of essentially define square root of x algebraically. So y is square root of x, and indeed, if x is defined, like this is intuitively, not indeed mathematically. At p, so is square root of x. Like locally, there is no problem defining square root. So this is an example. You see, that's why, like, so this is many more functions that are defined at points, like square roots and stuff like that. A bad example is this. This is not monic. And indeed, t here is like 1 over x. So like y is 1 over x. Actually, that like really is 1 over x. I don't know where to put it. I don't know what, this is fine. This is like weird. I don't know. Why is that? And indeed, x is defined at 0 and y is not defined at 0. So not being integral over k of x may give you poles. So x is defined at 0, but 1 over x isn't. So this like, claim is tight in this sense. You need integrality. You need this to be monic. Right, it's not a, right. There are functions that are not coming, there are more functions. Yeah, so let's prove it. It's a one-line proof, but it's a kind of a smart one. Well, it's like a 7-line proof. So, right, so we know that y is integral over kx. Let's see how we use it. So we can, take, because of the integrality, you can find like a monic polynomial over kx, right, that y vanishes out. So these are the coefficients. So let's say that these are polynomials in x such that right, y being monic over k of x means that there is a monic polynomial, so there is a 1 here, a monic polynomial over k of x. So these are the elements, the coefficients. These are also polynomials, I know. So it is such that this vanishes at y, so I wrote it like already substituting y. And we can assume y is not 0. I mean, if y is 0, then it has no poles and everything's fine. So assume, I mean, I want to show VP of y is non-negative. It's fine. Okay. So what we're going to do, that's the standard trick in these cases, is we are going to divide by y to the d minus 1, because you can, and move things around, like keep this and move all of the other summations to the other side. So y is minus fd minus 1x minus fd minus 2x y inverse minus I think I did it okay. Yeah, it's fine. Right, so I wrote y in terms of its indices. And now it's just a matter of just looking. So we know that VP of x, we didn't use it so far, is larger or equal than 0. I fix P such that this holds, and I want to show that for y. It's not, it's like it's not this implies that. It's like for every P this holds. Okay? So I fix a P and I'm assuming that. So remember what I told you, because of that, we know that also the polynomials have non-zero as non-negative valuations. That's what we did before about polynomials of a function. It's at least the evaluation of P of x. Or 0, because there could be a constant factor, but it's non-zero, it's non-negative. Okay, so all of these have positive coefficient, all of the x's. So now assume by contradiction that the VP of y is strictly smaller than 0. That's what we want not to happen. So this would be negative. Like if I do evaluations on that, this would be negative. This one, evaluation of that will be negative. And the valuation of that will be positive because it's y inverse. So it's strictly positive. All of those, even increasing. And the valuation of these are non-negative. All of those. These are polynomials. Right, that's good because, yeah. Because VP, right, I'm assuming it's negative for a second. Then this means that, okay, this side is, the valuation of that is negative. The valuation of each of the summands here is, okay, so there is the x, the f of x, and the y. So the f of x is non-negative, and the y is actually strictly positive, never mind. But by the strict triangle inequality, we know that this is at least non-negative. And it's a contradiction to the fact that the left-hand side is negative. Contradicting the triangle inequality, not strict, just triangle inequality.